Good afternoon. My name is Sadiq, and I'm a PhD student at the University of Lausanne. The title of it has been introduced by the coordinator. Okay. So I start with the outline of my presentation is from the introduction to the justification, the materials and methods, results and discussions, and for me, I'll be talking about the challenges and the conclusions. So, for an introduction, we all, from statistics, the weakness of most welded structures is fatigue. Statistically, it's responsible for at least 90% of failures in welded structures. And these welded structures are susceptible or vulnerable to uniaxial or multiaxial fatigues due to their numerous stress concentrations due to the welding. So, ordinarily, from the version graphs from this diagram, you can see that we have two major types of joints, weldings or joints in pressure vessels, which is the circumferential and the longitudinal. So most times analysis is done on these 2 points, these two major points. But for critical applications, we discovered there's a need to do multiaxial fatigue analysis so as to know where the influence of the fatigue on all the axes possible in the pressure tank. So this is an example of a pressure vessel that has failed due to fatigue. So this shows the importance of this research. So another thing about pressure vessels is that we discovered that the choice of welding process, be it TIG or submerged arc welding or laser, influences the strength of the pressure vessels, because different welding techniques bring about different weld geometry, bring about different heat affected zones, and they bring about different residual stresses and different weld defects and so on. For instance, a laser welded joint has a lower weld penetration than an arc welded joint. So, still on the introduction, we discovered that from literature that riveting used to be used for pressure vessels before, but nowadays it has now become different because welded pressure vessels are more leak-proof and stronger in terms of stronger than riveted joints. So there are organizations that have worked on this so as to design and ensure the safety of these pressure vessels. These are ASME, the European ENN 13445, and some other ones. But for this research, we discovered that under the ASME, there are two divisions, and division 1 is designed by rule, and the other one is division 2, which is designed by analysis. This division 1 is a kind of design principle that uses more material and uses thicker sheets to weld pressure vessels. So that's why this division 2 was introduced to reduce the thickness and make a cost-effective pressure vessel. So the basis of this research, we are going to look at this, how to use this division 2 to get more cost-effective pressure vessels. So for this presentation, I'll be talking on the FA analysis, the linear method which I used on the sample pressure vessel that was used for this research. So we'll be asking, why are we conducting research on this particular equipment? We discovered that if you are to get a pressure vessel, it requires a lot of man hours, and the conventional processes, welding methods, such as submerged arc welding, they are not, most of them cannot be easily automated. So laser, with the advancement of laser beam technology, it's found that you can automate these welding processes and reduce man hours on welding the pressure vessel. So as part of our inquiry, we want to check whether this laser welded pressure vessels give better fatigue resistance compared to the other welding techniques. So to do this, we are using a recognized standard, which is called ASPE, and we are going to do calculations with FEA and correspond them with the calculations from ASPE. So this is the proposed methodology for this research. We get the design data sheets for the samples we are going to use. For this research, we are using stainless steel 347 because it's good for applications that require high temperature and higher pressure, such as boilers and nuclear reactors. So then we do the stress analysis. We know the fatigue loading cycles. Then we assess the multiaxial stress states, and to the end, we validate them and get the reports. So the first thing we need to know before we do the experiment or the methodology is to know the basic points on welded joints on the pressure vessel. And according to us, we have 4 categories of welded joints: category A, B, C, D. So for this sample simulation, we worked on the circumferential joint, which is from this diagram is a category A joint, and we worked on the nozzle to shell joint, which is a category B joint. So to do this, we make some calculations to get the thickness we are going to simulate in the FEA analysis, and from this formula you can get this thickness, which is eventually stated here. So from the FEA analysis, we indicated the welded joints from the first picture, and after we applied pressure, we used an asymmetric analysis. We cut the tank into 2 parts, and we applied pressure inside the tank and place some fixed supports under the saddles and see the influence of the pressure inside the pressure vessel. So we're able to compute the total degree of deformation, the equivalent elastic strain, and the equivalent elastic stress. So afterwards, we now simulate, we extrapolated the fatigue sensitivity of the tanks, and we discovered that for the strain life fatigue sensitivity, the tank performed better for strain life activity. So from this analysis, if you are trying to design a tank, you could know when the kind of cycles you subject the tank to, whether it's low cycle fatigue or high cycle fatigue. So for the ones with the flat curve, they easily adjust to any changes to pressure, the pressure we apply to the pressure vessels. And another information we could get was the mean stress graph, and this told us the kind of mean correction theories that were used in the simulation. So finally, even though we discovered that we could get a better safety factor from this analysis, there are still problems on getting this results. Like, for instance, ASIS still cannot simulate laser welding processes very well because they are limited currently to spot welds. So I'm basically right now looking for anybody that has any software that can do this analysis, which is how to vary the laser power, welding speed, and laser beam dimensions on the strength of welds in better vessels. So another thing is that another challenge got discovered that other welding processes in FEA are still not up to date. Most of them are still one type of welding or the other. So there's a lot of room for research in this in FEA, the analysis of welded joints. So in the future, I plan to work on the crack propagation of laser welds in FEA. So with this presentation of mine, I think I've ended it here, and thank you for. And when we discuss recently, if I've seen further than others, it's because I've stood on the shoulders of giants. Thank you.